So we saw that first law of thermodynamics can be written in terms of an equation as the change in internal energy is equal to Q plus W, or Q is the heat added to the system and W is the work done on the system. Now if we assume that we're at constant pressure and there's only expansion work, then W is equal to minus P delta V, where P is the external pressure. And now if we solve the equation for Q, we see that Q is equal to delta U plus P delta V. Now this is fairly important. All we did is we took the first law, we made the assumption that we're at constant pressure and have only expansion work. And now what we have is Q in terms of two state functions. And so with this assumption, Q actually becomes a state function. Now Q is a path function, but again, if you make the assumption that constant pressure and no expansion work, then it becomes a state function. Now it's important enough that we actually call Q with these approximation as a delta H. And so the enthalpy is actually best defined as the change in enthalpy is equal to the heat transferred to the system under constant pressure and assuming only expansion work. And so delta H equals delta U plus P delta V. Now, this is a nice definition. Most chemical reactions take place in open containers and hence has a constant pressure. And so the assumption of constant pressure expansion work makes sense. Now, enthalpy is also a state function, so it's much easier to handle than heat, which is a path function. And so because state functions, for the change in state function only depends on the final and the initial state. Now, enthalpy itself cannot be measured in absolute terms, but the change in enthalpy again is just Q assuming only expansion work and constant pressure. And so if heat is transferred to the system, that would mean Q is positive, that would mean delta H is positive. Now if we think about it in terms of enthalpy, that means the final enthalpy is greater than initial enthalpy, and we refer to that as an endothermic process. And so that means heat is going to the system from the surroundings. Now remember that we defined our universe as being composed of the system plus the surroundings. The system could be our beaker. The only thing that can be transferred between system and surroundings is heat and work. And so again, endothermic means that heat is being transferred from the surroundings to the system, and corresponds with a delta H of positive, a Q of positive. Remember, delta always means change, and it's always final minus initial. And so you can think about it, initially our enthalpy is low, we add some heat and it raises the enthalpy. And so the enthalpy of the product is always greater than the enthalpy of the reactants when you're looking at an endothermic process. Evaporation is always endothermic. We'll see in a little bit that for a compound, the gas always has a higher enthalpy than the liquid. And so heat is a reactant. You should also remember that gases are always the most stable phase at high temperature for a compound as long as there's no decomposition. For a liquid to a solid, you have to take heat away, and so that's always referred to as exothermic. And so heat is a product. Now here we're going to have delta H less than 0. Again, heat's going from the systems to the surroundings, so Q is negative, delta H is negative. Again, delta H is just Q, assuming no expansion work and constant pressure. And so for exothermic process, heat can be treated as a product. Delta H is going to be less than 0. Remember that solids are typically the most stable phase at low temperature. And so endothermic, heat's added to the system, heat is a reactant. Exothermic, heat's removed from the system, heat is a product. Endothermic processes, delta H is positive, again Q is positive. Exothermic processes, delta H is negative, Q is negative. Delta H again is just Q, heat transferred to the system, assuming only expansion work and constant pressure. Now if we also look at it, the same reaction, so you notice the top reaction, you have water going to hydrogen gas plus oxygen gas. That's endothermic, delta H is positive, heat's being treated as a reactant. If we flip that reaction around, then we see we also have to flip the heat around. And so heat goes from being a reactant to being a product, or delta H goes from being positive to being negative. And so if we reverse the reaction, that changes the sign of delta H. If you multiply the reaction, that changes delta H. And so for that first reaction, if we multiply the entire reaction by 2, chemical reactions are like mathematical equations. You can multiply by a number. And so if we multiply the top reaction by 2, notice that we also have to multiply the heat by 2. And so delta H goes from being 285 to 570. If we take that top reaction, multiply it by 4, then we'll also have to multiply the delta H by 4. And so it goes from being 285 to 1140. And so this is kind of a cool reaction. We have barium hydroxide hydrate plus ammonium thiocyanate, and we just mix it. They're two solids, and they actually form an aqueous and liquid and a gas.
The water on this cork pad will freeze when an endothermic reaction absorbs heat from its surroundings, including the water and cork. The solids barium hydroxide octahydrate and ammonium thiocyanate absorb heat as they react, forming barium thiocyanate, ammonia gas, and water. A slurry forms as the two solids begin to react, because one of the reaction products is water. The waters of hydration are also released, forming an aqueous solution that allows the reaction to proceed more quickly. The temperature of the slurry drops to minus 15 degrees Celsius. The water between the cork and the beaker has frozen. Atmospheric moisture has also condensed and frozen on the side of the beaker. Reactions are either exothermic or endothermic, meaning that energy as heat is either released or absorbed.
And so for some, this is a little confusing. The beaker's cold, and that's why it's stuck to the cork. Remember that they put some water between the cork and the beaker. The beaker gets very cold, actually freezes that water. Now, the beaker's cold. Does that mean it's exothermic or endothermic? It actually means that it's endothermic. Because it's cold, heat will go into the system. And so if you have a reaction, the beaker becomes cold, that means it has to be endothermic because heat will go from the surroundings to the system.
If we combine one gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. A surprising amount of energy is released by the reactants, and in the process, their atoms and molecules rapidly rearrange to form the products carbon dioxide, water, and potassium chloride. The reaction is said to be product favored.
And so here our container got very hot, and so that means it must be exothermic. And so if the reaction vessel gets cold, endothermic because heat will go from the surroundings to the system. If the reaction vessel is hot, it means it's exothermic because heat is going from the reaction vessel to the surroundings. And so we went from gummy bear to liquefied bear. We released a lot of energy, and so we converted chemical potential energy into heat.